Hello guys, welcome back to my lab 6, magnetic molasses by Mantelis Benavichus. So pretty much the purpose of this lab was to compare data that we got from a bar magnet that we released down a conductive aluminum foil tube, and we used that data and pretty much just compared it to the simulation for the same situation. The code was used to model and analyze the same situation without the accounting of drag forces that could be present. And we were trying to find the speed of the magnet that's falling. And so what we ended up coming up with is that the in-person result was around 0.985 seconds and the simulation was 0.398 seconds. So we have a lot of different equations that we ended up using here. There was the Biot-Savart law that we used to find the magnetic field. Then we used that to find the magnetic flux. Then we used that for more magnetic field, I guess. And then Faraday's law, which used voltage, which we used to get voltage. And then Ohm's law, and then used that voltage and make it into a current to find magnetic current, and then use that and turn it into magnetic force that's on the ring or the bar. And there's also Lorentz force equation that we used, and there's a lot of different equations that came into play here. So the lab setup / procedure: the inner radius of the tube was 3.175 centimeters, the outer radius was 3.8, tube length was 47, and pretty much we just dropped the magnet down that tube as indicated by the arrows, and we recorded in the stopwatch 5 times the time that it went in and the time that it came out, and the 5 recorded times are below, and our average time was 0.985 seconds. So glow script code, pretty much what we ended up doing, or what I ended up doing, is I imported all the different values that we had that were constants up in the top left, as you can see with the different inner radius and outer radius and all that. And then when we go ahead onto the rest of it, we have pretty much just different calculations, like I said earlier, from those different formulas, with flux and trying to find the magnetic force, and all of that pretty much just ends up getting us the magnetic force, and then adding it to the gravitational force to counteract it. And yeah, that's how we end up creating our simulation. So it comes out with this velocity versus time graph along with the image to the right, which in the actual glow script, if I went into it, it would move up and down. But the blue portion of the bar magnet is counterclockwise current, and then the red is clockwise. Magnetic flux is decreasing and pointed downwards. If the magnet was flipped, then the top would be clockwise and the bottom would be counterclockwise. The real speed of the drop was about double that of the computation, like we said earlier, and the primary reasons for this are just because we could have failed at hitting the start and stopwatch when we needed to, and also not accounting for drag in the simulation. And then the graph to the left pretty much just says that the acceleration due to gravity is still pretty present, despite the magnetic force also acting. So for what if and what does it mean? What if? So the resistivity, the conductor, were reduced as close as possible to 0. How would that affect the dynamics? Pretty much the current would then be super large, which would heavily increase the magnetic force and would slow down the magnet even more because there would be more stuff to counter force of gravity. And then for the what if, what would happen if there was holes or slots? It pretty much would just cause a change in the direction of the magnetic force because it wouldn't go straight up anymore. And that would mean spinning of the magnet within the tube just because there's no longer, it's a changing direction for the force. Thank you.